Okay, so before we start the second hour of lecture, I have a kind of a favor to ask. 希望你们帮个忙啊 I have a favor to ask. So you know that the university, 我用中文好，行政上面，它学校在推动英语授课，当然我们这个课也是英语授课啊。那所以最近这个学校的校务研究中心跟教务处，我有在教务处兼任行政职，所以也是我们希望说。特别请大三的同学，如果你们有修英语授课的话，我们也出了一个问卷来帮助我们评估的学习成效啊。所以那我身为自己本身也是英语授课的老师嘛，那我想说填问卷，大家应该学期末都会被塞很多问卷。我听说啊，有各种的处室单位都会叫你们填问卷，包括教学建评的。By the way, please remember to do this. Okay, let me know. Where I can still improve, my team can still improve. Please let me know regarding that. But there's a separate questionnaire. 有个另外一个问卷是关于叫做英语授课 EMI 啊。那个问卷的话，如果你们愿意的话，可不可以麻烦帮忙一下？大概3到5分钟啊。如果愿意的话，我把那个 email 的连接，你们应该没有收到，有收到吗？有收到是？好，那我个人觉得说这个就当作是相逢就是有缘分。我准备了7本书啊，如果头7个完成问卷，请跟我要1本书啊。好 ，I'll announce it. Yeah, so I pick up a few old books from my shelf. 书架上没有在看的书啊，我觉得说，与其一直放在我书架上，那个还不如就大家交个朋友哦。这样我就可以再去买新的书。So I prepare 7 books for this purpose. Or any question regarding お願いします啊，请麻烦大家ください啊。好 ，So yeah, so during the break, one of you came to me and asked questions regarding details of this plot. Very good questions. Okay, so I want to share with you. So 哪一位？这位后面这位啊，这同学。So you said that you notice that there's some peculiar things. Here we have a white patch. 有一部分好像白白的，对不对？There's a white patch right here, and maybe also right there. Also, most notably, like above 16 kilohertz, everything's white. So what's going on right here? What's going on right here? What does it mean to suddenly have some empty places? White meaning that there's no signal, right? That like these pixels are replaced by the white pixel by 0. Okay, what's going on? So very good observation. Okay, very good question. And I need to tell you that when I saw this first time, I was surprised too. But later I realized this is because of format. Okay, this is I just took my cell phone to the MRT station and I started recording. But the storage format was MP3. Basically, it's compressed. So you guys probably have heard that MP3 achieved compression. 它达到这个 compression. Achieved compression by a few tricks, and one of the tricks is to throw away unimportant signals. So let's say the MP3 also does an analysis of a spectrum. Look at the part of the spectrum and see that this part is not important. Let's just discard them, replacing this part of the spectrums with 0 to save your storage place. So that's one trick. I'm pretty sure that's what's going on. Particularly maybe everything above 16 kilohertz. I don't think this is the result of analog low-pass filtering. But I think probably after converting to digital, before saving it, before saving the file, my iPhone decided that they look at the spectrum and see that these are not important. It doesn't, even if we store them, it wouldn't affect your hearing. They cannot be heard. Even though the signal is there, its frequency is too high, you cannot hear it. Let's just set all of them to 0. I think that's what's happening. So very good observation, very good question. Okay, missing stuff. If you just record using C2D without compression, you should not expect to see anything like this. You should not expect to see missing pixels. It's almost impossible because the background is always full of noise, right? Noise is broadband. So you never expect to see a natural spectrum to have like white patches like that. Okay. That's probably due to compression, right? That's my opinion, okay? All right, very nice question. So now let's study how the plots are actually generated. Yeah. Because here, please note that even though the time, short time Fourier transform as defined right here, as the definition goes right here, the frequency is continuous. So in one or another, in actual computation, we need to discretize frequency. You cannot compute frequency at every possible real frequency, okay? It's not something that we can store in digital format, right? So somehow we need to discretize, we need to discretize frequency as well. And the correct version to use is called the discrete Fourier transform, or DFT. So let me go back and tell you what is DFT. So now DFT right here, okay? Here we have a definition. We begin with the assumption that we have a block of signal which contains L points. Begin with one block of signal still in time. So time goes from 0 to L minus 1, a total of L samples. Okay. So, but in this notation, by the way, this is my handout, right? So the notation might differ from the textbook, but the idea is the same. So here I'm denoting the block as a column vector. Okay. So S0 to SL minus 1, we have a vector, an L-dimensional vector. That's a way to look at the block as a column vector, right? Transpose. Okay. So far, so good. Now, a block of signal can be viewed as a length L, as a column vector of L dimensions. Yeah, so far, so good. One block of signal. And now, then we can define this DFT, the discrete Fourier transform, as a discrete kind of spectrum denoted as big X, bold font, 2 to the S, which also contains L points under this equation. Okay, so let's take a look. So here, K becomes the frequency index. Is that clear? K is a frequency index. And K goes also from 0 to L minus 1. So we have a length L signal, then we are evaluating the spectrum at L frequencies as well. L points in time, L frequencies in the frequency domain. Yeah? So K is a frequency index right here. And so here you see K shows up in here. K times 2 pi divided by L is the actual omega. The discretized frequency equals to K times 2 pi divided by L. That's omega, right? So usually when you look at the Fourier transform, you see the signal inner product, right? What's been multiplied? Usually you see exponential j omega n, right? So here omega is replaced by K times, if you will, the fundamental frequency, okay? 2 pi divided by L. Yeah, so take a look. So you really, we want to contemplate on this definition. Okay, K times in time, K points, K samples in time, K points in frequency. No, not K, L. L points in time. L frequencies in the frequency domain, okay, indexed by K. So let's explain why this is called discrete Fourier transform. The terminology could be confusing, right? The Fourier transform, the discrete time Fourier transform, but now to further confuse ourselves, there is a discrete Fourier transform, DTFT, DFT, or simply FT, right? So why is this version called the discrete Fourier transform? Because discrete Fourier transform is the DTFT sampled in frequency. The spectrum was continuous in frequency, but now we sample in the frequency domain. We sample DTFT. Okay, we sample, not here, yeah. Basically, the idea is to sample DTFT in the frequency domain. So now the frequency also becomes discrete. And that's why we call it the discrete Fourier transform, because the frequency now is also discrete. Time is discrete, frequency is also discrete. Okay? So that's in terms of the terminology. Okay? The reason why we call it discrete Fourier transform. So let's take a look. I have a few kind of visualizations right here. So here, for example, let's focus on left. Okay? So that's the very definition we had in the previous slide. A block of signal which has a length L, and we are evaluating the spectrum at exactly k times 2 pi divided by L, and the result is denoted as big SK. Frequency also becomes discretized, right? So you can imagine that it's equal to dTft but sampled at this omega equals to k times the fundamental frequency, or 基础频率 if you will. 2 pi divided by L. We say S of omega evaluated at omega equals to k times 2 pi divided by L. I call this the fundamental frequency. So my insight that, dTft, as we all learned it, you should be familiar now that dTft is periodic. Every 2 pi, it repeats itself every 2 pi, right? So in this sense, we can say that dTft is the transform defined on the unit circle. Right? We talked about that already, right? If dTft exists early in the semester, right? So dTft is the transform sampled on the unit circle, evaluated on the unit circle. But then now further, dft is dTft evaluated on discrete points. So in this plot, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points if our signal has a length of 9. You see what's going on right here? If our signal has a length of 9, a block, if the block length is 9 samples, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we calculate dft using this definition, we obtain 9 frequencies. 1, 2, 3, 4, 5, 6, 7, 8, 9 frequencies around the unit circle. Whereas if you compute the dTft of the entire signal by adding 0, by assuming that elsewhere the signal is 0, that's the most reasonable assumption. We say a block has length 9, and then when you want to calculate the dTft, so if we assume that everywhere else the signal is 0, then you calculate dTft, it becomes continuous. It's a continuous spectrum for that. And by doing that, then there's a relation between dft and dTft is that dft is dTft just sampled in frequency. Is everything making sense? Everything making sense? DFT. That's why. The reason why we call it DFT. Okay. Because it's dTft evaluated at discrete frequencies. Okay. So with that in mind, we've seen that I try to argue that DFT is dTft sampled in frequency. And the other way around is saying, you can say the opposite, actually. You can say the opposite, that what is dTft? dTft is DFT interpolated in frequency. Let me say that again. If DFT is dTft sampled in frequency, right? The other way around also makes sense. We can say that now dTft is DFT interpolated in frequency. Just going between discrete and continuous, okay? That also makes sense, okay? I'm not going to emphasize on this notion. 这个想法，我想先不要过，因为今天第一次接触。I don't want to overemphasize this notion, but kind of the converse is also making sense, okay? Also makes sense. If one thing is the other thing's sample, then that other thing's this thing's interpolation. 一个是取样，大概就是内差嘛。我就当代你 time domain a lot but now we sort of have the situation of doing everything in the frequency domain, right? But what I want to emphasize, I do want to emphasize that DFT is very simple. DFT is nothing but DFT sampled in frequency. That's for sure. Okay, that's for sure. Easier to understand. Okay. Can I move on? So this, I just want to bring this up a little bit. All right. So now, more important thing is this concept. DFT, right? DFT is a linear transformation. That's probably the more important message I'm delivering today. Okay, DFT is a linear transformation. You take a column in time. And then the corresponding transform can be represented as a matrix. So DFT is really a transformation from an L-dimensional space to another L-dimensional space. The source space is in time, the target space is in frequency, okay? And the transformation can be represented by directly by a matrix. We know that. Linear transformation can always be represented by a matrix, okay? So let's take a look. If small s is in time, big S is in frequency, which is defined as the L frequencies, L samples in the frequency domain, transform, also column vector, okay? Then we can establish, we can construct a matrix, and you can check that this is correct. You can check that this is correct. So you have a small s. If I emphasize it's a vector, small s0 to sl minus 1, which is usually in the real L-dimensional space. And DFT takes it to the frequency domain, S, big S, okay? Big S. Now, is in the frequency domain, also L-dimensional, okay? With this, and you can easily check that DFT is linear. So therefore, any transformation, linear transformation from L dimension to L dimension can be represented by an L by L matrix. Okay, L by L matrix. So S equals to, if you call that matrix F, so you can just construct an F such that this transformation now is represented by F. Okay? So let's take a closer look. Here F has a nice organization. It's all 1 right here. And then 1, if I have this factor W, okay? If I define W as this, nothing to do with a window, okay? W is just a complex number. If I define W with this factor by e to this minus sign j 2 pi divided by L, so and then we have a very nice organization. It's 1W, W square, geometric sequence for each row, right? The next row is 1W square, W fourth power. Okay, so that's the next row, and so on and so forth. The last row looks like that. Very nice organization. And so to compare, you just check. Do we really have Sk equals to summation n from 0 to L minus 1, Sn, what? E to the minus j k 2 pi divided by L n, right? Yeah. So take a look. This is our original definition, and this is a matrix representation. They are saying the same thing, basically. So that basically so you need to ask F. So when we multiply, the trick is to notice that when we multiply a column vector with a matrix from the left, we essentially are doing inner product, right? We're taking the inner product of one row here with a column vector at each time, right? So that's what we are doing. That's what we're doing. So when you say, and what is inner product? Inner product is a summation, is the summation. Okay? So you're taking the inner product, you're summing one row, element of one row with element of your time domain signal each time for each frequency. You pick a row, do the inner product, and the result is one element in the frequency domain, right? Every element in the frequency domain can be calculated by the inner product, taking the inner product of one row right here with your time domain signal. So it's a linear transformation. So this is like one key notation I want to bring up to you. Fourier transform DFT now can be nicely written in the matrix form. Very nicely written in the matrix form. So is it making sense? Inner product and so on, right? So it's a linear transformation, and it's full ranked. You can check that. So therefore, you can also find the inverse Fourier transform. But here I want to make a few more remarks. First of all, as I said, DFT now with this matrix representation is really, what it really is a linear transformation. And secondly, if you take a look at the matrix right there, you will very soon realize that rows of the matrix, or columns equivalently, they are orthogonal to one another. They are mutually orthogonal. Mutually orthogonal. First of all, this matrix is symmetric. Did you notice? This matrix is symmetric. So row or column doesn't matter. The columns right here, let me say rows. Every one row and another row, they are mutually orthogonal. So basically, now you can imagine that we now have L orthogonal vectors for the space. And for every signal in that space, we are basically doing a change of basis. Fourier transform is the change of basis. We're projecting our signal onto this using the new basis, 用新的基底啊. And they're orthogonal. That's a very nice property. Orthogonal basis is a nice property. It's very nice to obtain an orthogonal basis for your space. Just like XYZ, right? Mutually orthogonal. These rows form a complete orthogonal basis. Is complete. It forms a basis, or orthogonal basis for our space. Every row and any row and any other row are mutually orthogonal. So they are just like XYZ, mutually orthogonal. So which makes them very convenient for calculating the projection. When you have an orthogonal basis, it makes that makes it convenient for calculating projection, right? Because when you do inner product, initially you're doing the decomposition already. 只要算这些内积 you're doing decomposition already. 已经把它拆解成这些向量了。所以这个 linear algebra notion in Fourier transform I want to bring up. Okay, any comment? 这样有清楚吗？ Fourier transform is easier to explain when we go discrete. Just an L by L matrix, very straightforward. Okay, so this is matrix representation for DFT, and the matrix is an orthogonal matrix with rows being mutually orthogonal. They're 正交的啊，中文啊 linear transformation, and so therefore, as I explained, DFT is a projection onto a new coordinate system. DFT it is, it is a projection, 是一个投影啊 onto a new coordinate system, 一个新的坐标系啊，一个新的坐标系。A projection onto a new coordinate system, and this is what we're doing. Suppose that we want to evaluate big S at this frequency, right? Taking this one, this second element, for example. When you want to evaluate the spectrum at the first frequency, what we're doing, you end up doing, you're calculating the like product, sum of products. Sum of product. You have your signal as a column vector, and you take this second row and calculate the inner product. Yeah? Or should I say calculate the sum? Because inner product is a projection. Yeah. And the result is the result being the spectrum at the first frequency. Yeah. And we have a few notes right here. Each row represents a basis vector. Okay? And we calculate their inner products with the signal. Yeah. The Fourier transform now apparently is a change of basis from time to frequency. It's a change of coordinate. It's a projection onto a new coordinate system. And that's what it means to go from time to frequency in terms of linear algebra. Okay? All right. So that's an important idea I want to bring to you. Okay, Fourier transform, the discrete Fourier transform is a linear transformation, and naturally it has a matrix form. It has a matrix representation. You can represent the transformation using an L by L matrix. Okay, are we good? Are you still alive? So how does that relate to the short-time Fourier transform? Okay, so computationally, we are not going to evaluate the spectrum at all the omega right here. We are going to discretize so we are going to discretize and look at k discrete frequencies right here. So that's a connection. Okay, all the plot that you are seeing before, all the nice plots, spectrograms, if you just look really closely, the frequencies were evaluated only at discrete places. Okay, maybe 1024 points. Yeah, they are discrete. The spectrums are discrete. But now the next topic I want to bring up is that the fast Fourier transform. Okay, yeah. Bear with me, fast Fourier transform is actually nothing but a fast implementation of DFT. Okay, so let's try to recall all the terminologies, right? What is DTFT? DTFT is Z transform evaluated on the unit circle. Okay, and what is DFT? DFT is DTFT evaluated on discrete frequencies. Okay. And then what is FFT? FFT is nothing but a fast computation for DFT. Okay, it gives you exactly the same result but faster. Is that easy? Is that clear? FFT is nothing but DTFT but fast, right? But with a greatly reduced computation load. So let's try to take a little bit of a look. So regarding the computation load, okay, so recall that now we have a matrix representation for DFT, L by L. Okay? The question is, how many multiplications do we need to accomplish one processing of one block? You want to just go from time to frequency domain, L points in time, L point in frequency, can we agree that this involves L square multiplications? Maybe floating point, L square, right? Because summing the product, summing the product, summing the product, okay? For each element, it takes L multiplications. As well as summation. Then so if you go completely from time domain, L points in time, L points in frequency. Roughly speaking, direct computation of the Fourier transform involve L square multiplications. Roughly speaking, that's the order of computation load. 乘法要算 L 平方次啊，大概是这样。It takes L square multiplications to complete one block, processing of one block, okay, to go from time to frequency. So historically, people has asked, is there any way we can reduce the computation load? And the answer is yes. And the result is famously known as fast Fourier transform nowadays. Okay, faster. Actually, it turns out that you don't need to spend you don't need to calculate L square multiplications. You can reduce the computation load. And tell you the result first. It turns out that it's possible to reduce the computation load from n squared to n log 2n. And that's a lot of saving the time, saving the computation load. A lot of reduction from n squared to n log 2n if n is large. Okay, if n is large. And this, any trick that completes Fourier transform in n log 2n of the computation is generally referred to as FFT, fast Fourier transform. Generally, the computation load is in the order of n log 2n. Instead of n squared. Here n being the length of the block, okay, which is denoted as by L previously. Now, n being the length of f of t. Okay, the paper was published. Let me mention that the paper was published in 1965. 1965, before you were born. And also before I was born, long time ago, 1965. 1965, well, before human landed on the moon, if you will, 民国54年 before the College of ECS of 清华大学 before Department EE, OK, 理学院可能已经存在啊，电子学还，工学院可能 I don't know， 电机还没有啊 ，before 新竹科学园区for sure. Long time ago, it's often named as one of the 10 most important algorithms in history. Often. So sort of as this suggests, okay, n log 2n. So we'll see in a moment that the algorithm is most efficient if n is a power of 2. Let's say n is 1024, which equals to 2 to the 10th power. 如果是2的完整次方数的话，通常会比较有效率啊。We'll see in a moment why. Okay. Any question regarding the kind of summary for the paper? Often named as 110 of the most important algorithms in history. And its original algorithm is most efficient for if n is 2 to a power. Anybody want to guess what other algorithms are among the 10 most important? 有听过这个说法吗？我没有很仔细想。What other algorithm you have learned can also be listed as 10 of the most important algorithms? How about Parks-McClellan algorithm? No. What other algorithms are also most important? Can you read it? 好，我只有学过 quicksort. Okay, I'm not an expert in this domain. Please take 韩永凯老师演算法。I've heard a lot of good words. Right? 10 so this is listed as, if you will, one of the 10 most important algorithms in history. Okay, and let's take a look how the structure looks like. So the idea is divide and conquer. We're not going to go through all the details right here, but if you take a look, what's going on? On the left, we have everything in the time domain, small x. On the right, big X. Okay, yeah, that clear? Yeah. Time to frequency. And now you have routes. The signal goes to the right and also crisscrossing. Okay, so there are, if the length of FFT is 16, which is 2 to the power of 4, right? Or 四次方, right? So you see that just merely by inspection, first we divide. First we have a kind of 8, 16, all 16 to 16 sort of crisscrossing. But in the second stage, what's happening? In the second stage, we are sort of dividing our routes into 2 blocks, right? 2 divisions. This is a one full thing, but then now this 16 is divided by 2. Now the result is 8, right? We have a division of A samples right here, N sample right here. Yeah? So divide, and then we can further divide 8 by 2. Now we get 4 blocks of 4 sample operations. Okay, so one block of 16 sample operation, 2 blocks of A sample operations. Now 4 blocks of 4 sample operations, right? And finally, the 8 blocks of 2 sample operations, and this is just plus and minus. At this point, if I remember correctly, everything that goes down is -1. Everything that goes up is +1. Okay? Divide and conquer. But there's an important detail right here. In the detail, this is where we have multiplication. Otherwise, just plus or minus. Okay? So now you see that everything here, the multiplication happens in between stages. That's an important detail to pay attention to. Okay? So now we have in between every 2 stages. Before we go on to the next stage, we need to perform 16 multiplications by these factors. What is W? W is the W I just mentioned. W is that. W16 is e to the minus j 2 pi divided by 16. And W8 is e to the minus j 2 pi divided by 8, and so on, right? So these are places where we need to perform multiplication. Otherwise, everything else is just plus or minus, adding or subtraction. Is that clear? Divide and conquer. And don't ask me how to come up with that. It must be genius. That's why this is one of the 10 most important algorithms. It's not trivial at all. I don't find it trivial at all. 我觉得并不是非常的显而易见的。Back in the history. Very nice algorithm right here. So let's count the number of multiplications, shall we? Yeah? 数数看有多少个乘法 Shall we? Yeah. Let's count how many multiplications we have right here. 多少个16啊？对，4 stages, right? 3 times we need to compute 16 multiplications. So what's that? So we have 3 times 16 equal to 48 complex number multiplications. Okay? What is 3? 3 is log 2 of 16 minus 1. It's actually log 2 and minus 1, even better. And what is 16? 16 is n. Okay? So the computation load is in the order of n log 2 and actually minus 1, even better for this design. Okay? So that's how divide and conquer helps computing Fourier transform. 觉得有 nice 吗？这个还蛮 nice 的Any question? Any question? 今天应该差不多，就后面只剩一点点后面只剩一点点。我们先讲这个地方So as an example, the longer n is, the better saving you achieve. Okay? n 越高的时候，那个 computation 的降低量是越显著。Okay? It's more significant to go for a longer n. Okay? For example, if length of Fourier transform is only the block length, if it's 8, then it takes 64 multiplications to complete the Fourier transform without knowing FFT, just using the matrix. A squared is 64. Okay? So similarly, if the length is 64, then 64 squared is 4,000 something. Okay? If you use a direct matrix representation for calculating the Fourier transform. Okay? If your length is 1,000, then it's 1 million. But now to compare, if going for FFT, n log 2n equals to 224, 300, or 10,000 for the 3 cases. So how much do we save? How much computation do we save? You get a feeling, right? So now it probably doesn't save so much. Reducing the load from 64 to 24, it's okay. It's kind of cool. How about reducing from 300 to, reducing from 4,000 to less than 400? Already you have a 10 times saving, okay? By using fast Fourier transform. Even more, for 1024, you don't want to use the full matrix, okay? Please divide and conquer. Then you have 10 stages with 9 layers of multiplications in between. And your computation is just slightly around 10,000, which is about 100 times saving in terms of computation load. Okay? Significant saving. Okay? So that's why it has a lot of impact. That's one extra thing. And in here, I'm showing just in the textbook. If you're super interested, refer to the textbook. There's an entire there's an entire chapter devoted to fast Fourier transform. There are different architectures. There are different architectures. You can divide and conquer, or I don't know, how do we call it? Merge and proceed. 2 to 4, 4 to 8. You can go the other way. There are different ways to implement that. So this is one of the many implementations. Similar computation load. Okay. So what else do we notice? What else do we notice? Anybody? What else do we notice right here? One thing I noticed, and I found it puzzling, okay? I want to point it out before we end today's lecture. On the left right here is x0 to x15, right? On the right, what is the order? What the heck is this order? It's 0, 8, 4, 12, 2, 10, 6, 14. What the hell is this order? How do I memorize this? 我给大家1分钟记得这个 sequence 请把它背起来啊！1分钟背一下，08、42、20，等下抽考就有点。It puzzled me. Okay, it really puzzled me. How do I figure what the heck is this order? By going to frequency now, fast, but the order is like random. Could that be problematic? You know? 只要记一半 ，How come？ 有吗？哦，你有发现这加起来15是？哎，真的？哦 ，good。好，那大家请记这一半。那来，然后呢，这半有什么 trick？ 因为加起来14，那你只要记4个，是这样子吗？哎，你们都太聪明了，好聪明了，比我聪明啊。So there must be some trick in how this is ordered, okay? But I say the textbook tells us, okay, or any other comment, what this is about. Now you just only need to 记得08，是不是？是这样吗？不对，不是，你还是要记得第二个是8。你希望我卖关子还是现在就告诉大家？我卖个关子啊，这蛮有趣。因为 I think the entire architecture is beautiful. Yeah, it must have something to do with the fact that matrix is highly organized. That matrix is not random. the matrix form, if we go back, the matrix form is pretty nicely organized, right? So it has something to do with the organization. People have been so clever to discover that we have such kind of this divide and conquer architecture, or merge and proceed 合并再前进 divide and conquer 这我随便编的名词 I don't know So maybe I should end my introduction right here and leave it to you to figure out what's going on. How do we just correctly identify? So it might be easy if the length is 16, but how about if the length is 1024? Right? The last, how do you organize the frequency bin to finally be able to plot a spectrum? Okay, so that's not trivial. Okay, it's important, not trivial and also relevant. 其实是蛮重要的，对不对？好，那 so I guess that's all I want to say about short time Fourier transform converting your signal to an image. And then the definition involved shifting your signal, keep shifting it to the left. So you are viewing your signal by using a window to take a block. So since we're taking a block, so computationally what we actually do is a short time, is a blockwise processing. And now the definition of Fourier transform has to be revised. We have a discrete Fourier transform, which enables us to calculate short time Fourier transform, a discrete version. And the discrete version can be implemented efficiently using any such kind of architecture. Okay, so that will be the summary, and thank you for being here.